we'll be looking at the isSameTree problem and build a solution in JavaScript while also computing the time complexity and space complexity of our solution. Let us understand the problem statement before jumping into the solution aspect. We will be given two binary trees. One will be represented as P and the second one will be represented as Q. We have to figure out whether they are equal or not. What do you mean by definition of this equal? Equal in the sense that, let's say this is the root node, value is 1. This one is equal to the one in the second tree as well. Then the left node on the first tree, which is 2, has to be equal to the left node on the second tree. The right node on the first tree, which is 3, has to be equal to the right node on the second tree as well, and so on as long as we have the tree. So this is the aim, and if it is equal, then we are supposed to say that the outcome is true. Otherwise, we will be returning false from a problem statement. Let's see how it looks in terms of visualization. I get the head of both these trees. I will compare this one and this one. It is same, all good. Next, we check the left node, which is 2. The right node is 3. The left node on the other side is also 2. So this is also passing the check. The right node is 3. The right node is 3. So all the three conditions, 1, 2, and 3 are being satisfied, wherein the values are equal. And this 3 checks will ensure that both the trees are equal. Now let's see how this looks in terms of code. So we said that the first node, which is the root node that we have received, they have to be equal. Now we have to take care of the edge cases. What will be the edge cases? We can receive the first node as null here and the second node also as null here. That would mean that both the trees have head pointing to null. In that case, we can say both of these trees will also be equal. But if one of them is not null, let's say 1, and the second one is null, then they won't be same binary trees because they have different root values. So this can be represented as something like this. Both of these are pointing to null and they are equal. I will just return true from my logic. Now the second case wherein one of them is null, then we can say return false, because if one of them is different, which is null, then it's not going to be the same binary trees. Then comes the part of adding our 3 checks. The first check is checking the value itself of both the nodes. So we will say return p.value is equal to q.value. So this will satisfy our first condition. If both of the values are equal, that would mean that the binary trees are satisfying the criteria from the first condition, which is the value itself has to be equal, and then we will check the left node and the right node. Now after we check the root node value, time to check the left node, and to check the value we have to pick p.left and q.left, both of those left values that are existing, and we will compare this values that we have. So we have 2 and we have 2, but there's a catch here. I cannot just check it at one level, because let's say the tree in this case was just going up to one level, but we can have another extension here which can go to the next level as well. So this can also have extensions. So we cannot just check at one level and say it's going to work. And because of that, the recursion part comes into picture now. And we will just call the same function again with p.left and q.left. This way we will check 2 and 2 again by passing this as the head now and this as the head, and then it will go inside and will check, hey, p and q both are not null, p and q both are valid, and the value of p.value, which is 2, is going to be equal to value.q.value, which is this one. So then it's going to return true. For the right nodes also I will do the same thing, wherein I will say p.right and q.right. So I will do the same comparison between the right hand side nodes also. And that's pretty much it in terms of implementation. This will go in a recursive call. It will keep checking for the root node itself, the first condition, then it will check on the left hand side, and then it will check on the right hand side. And that's the outcome of the solution. And in the end, we are just returning whether it is true or false. And at any point the values don't match, then we're just going to return false, because there is a AND check here. So all the conditions have to be met. And that's pretty much it. Now, in terms of the time complexity that is going to be involved here, it's going to be big O of n. Why big O of n? Because let's say we have n nodes. Let's say we have 3 nodes. It will check the value for this nodes. It will check the value for this and also this. It has to check all the nodes to make sure that the trees are similar. So you cannot just skip one node. In the worst case, when all the nodes are matching, in that case, it's going to be big O of n. Let's say maybe the trees are not matching, and at some point you found out the values are not same. Then it will be big O of n minus k. K being the point wherein the matching is not going to work out. So it's like 1 is going to be here, let's say, and here it's going to be 3. So it's not going to match. But in that case, it's like the best case scenario. But in worst case, it's going to be big O of n. So that's why the time complexity is also going to be big O of n. And in terms of the space complexity that we are going to have, that is also going to be big O of n, because we are going into a recursive call. As we can see here, we are doing one recursive call for the left hand side, we are doing one recursive call for the right hand side. And because of that, it's going to occupy in the call stack space. That space will be equal to the number of nodes that we have in the worst case. So it will keep on going inside, down in the depth of the tree, and then you will just keep popping the stack as you start returning values from the recursive calls. And that's pretty much it. Thank you for watching. Please like and subscribe.